Well, welcome back, everyone, and it's a pleasure to have Nicolas Bergeron giving his second lecture on the Czech cocycle, and take it away, Nicolas.
So today I will talk about the topological construction of cocycles, the second part. So let topological construction of cocycles, second part. So recall that, so let me briefly introduce what I will say today. So yesterday, recall that in the affine case, what we did yesterday is to construct a class which I called S affine inside in the equivariant cohomology with respect to GLNC in degree 2n minus 1 of Cn minus 0, and then explain that I can associate to this equivariant cohomology class a cohomology class of degree n minus 1 of the group GLNC made discrete with values in the meromorphic form on C to the n. And my goal today, I mean, I have two goals today, is first to revisit a little this construction and explain exactly how to erase hyperplanes. One crucial thing to go from this class to this class was to restrict the first one to Cn minus hyperplane. So I will explain how to do it and explain that in fact there are two ways to do it, and give an explicit expression for this class S affine for cocycle representatives of this class, and then to move on to the other cases, namely the multiplicative cases, where we now let only GLNZ act on the product of multiplicative group, or the elliptic case where GLNZ act on product of elliptic curve, and this will lead also to some natural cocycle, but cocycle of GLNZ. So that's my goal today. But first, I go back to the affine case. So back to the affine case. So again, from now, in that case, G will be GLNC made discrete, and so recall that our construction started by considering the term class of the universal bundle E.g. cross G mod Cn over the classifying space BG of GLNC made discrete. And then I said a bit quickly yesterday that, I mean, that's true, but it deserves maybe more explanation, that this bundle is a flat bundle, and therefore it has, I mean, the corresponding Euler class, which is equal to the Chern class of this complex vector bundle, vanishes because the bundle is flat. But I know some of you have reacted to this because I have a SPY in the afternoon session, and you're right. It's a bit. I mean, I said, okay, how do you prove that? You consider the connection of the bundle, and because it's flat, the curvature is 0, and so the class is 0. But here we are working over BG, which is not a manifold. So what does it mean to consider connection? I won't give much detail to this, but just to add some face to this statement, I want to say that there is some kind of de Rham theory in this setting. It's called the simplicial de Rham theory, and in fact, you can consider k differential forms on simplicial varieties like this, for example, on EG cross G times Cn over G, or the same on Bg, and such a k form will be a sequence of forms, of differential forms, on the product of the k simplex, so the sequence will depends on k, cross EKG cross Cn in the first case, or cross BKG in the second case. So recall that EKG is a set of k plus 1 tuple of element in G. So now each time you see a k plus 1 tuple, you put, that's how you do the geometric realization. You put a k simplex, and on this k simplex here, you use bicentric coordinates. And then you can consider differential form on this product. So if you take dk times bkg, it's just a differential form on the k simplex, because it's only a set of points, this bkg, and you want this form to glue along the faces using the gluing map that I have described last time. If you consider the first product, dk times ekg times cn, then you have a differential form in the, you have variables on the dk, and delta k, sorry, and you have variable in the complex fiber cn. And you can consider a differential form on these, and again, you ask them to glue along the faces of the simplicial complex. And so it gives meaning to what is a k differential form on these weird spaces, and a theorem that is due to Johann Dupont. There will be another Dupont, so I have to put his first name. Tells you that in this context, you have a de Rham theorem. So these differential form indeed compute the cohomology, and then you can work all the usual differential, differential topology construction, and in particular, you can consider connection, compute their curvature, but because BG is just a set, in fact, there is no curvature on the base, and that reflects that we are considering, in fact, flat bundle, and so the differential form representative for the term class vanishes, and that's why you can find, you can lift the Euler class vanishes, so we can leave the term class to what I've called last time S affine, and now it's a 2n-1, a degree 2n-1 cohomology class, so equivariant cohomology class on Cn-0. So I go a bit fast now, because I don't want to make a crash course on simplicial manifold, and in fact we will revisit this construction in a more explicit term using the locally symmetric space, and see how in practice how to avoid how to almost avoid simplicial forms. I will describe this in the first lecture, but from now on I just want to tell you, okay, you believe me when it's manifold, you can do essentially the same thing when it's in the simplicial setting, and that's where the class comes from. And now I want to start from this form and restrict it to Cn minus hyperplanes, and there are two ways to erase, at least two natural ways to erase hyperplane. and I will describe both.
Sorry, can I just ask to see if I understand? So this class is pulled back from the version where G is not made discrete. Is that right? It's pulled back from a covariant class.
That's for the moment no, but that's how we will relate it to the symmetric space later. But for the moment, G is really made discrete everywhere.
Right.
Okay.
But I'm just saying that this comes by pullback from the version where G is not discrete, or where GLN is given the usual topology.
Can you say it again?
I'm saying you can make an analogous instruction when G is given the usual, when GLN is given the usual topology, and this is the pullback of that one.
Yes, I will explain this later. Yeah.
Thank you.
But yeah, for the moment, I haven't done this. Yeah. Okay, so what is the first thing is you erase translates, GLNC translates of the hyperplane kernel of fixed linear form, let's say E1 star, or in other words, kernel of the product with E1. So that's the first natural set of hyperplanes you can consider, G-invariant set of hyperplanes. And another thing you can do is erase spans of translates of a fixed vector. You take a bunch of elements in G, and you consider the span of E1 by this bunch of elements. Of course, you have to take less than n-1 element to. I mean, you cannot take a linearly independent element if there are more than n. But I will explain this. So that's the other way to erase translate. So to do that, I will associate to any element G in G. We associate two types of vectors. The first one corresponds to the kernel of to the translate of kernel of E1. Then you translate E1 by G transpose, and I will denote it sigma. And the other one is the first column of E1 of G inverse is Q. And so from now on, when I denote sigma, is the vector is corresponds to translate by G transpose of E1, and Q is the translate of E1 by G inverse. And now recall the action of G on EG cross Cn. How we build the equivalence relation here. The action was given by G acts on X comma Z as X G minus 1. So X is a tuple of element in G, GZ. And this action, it preserves both the set of tuple. This is an element in EKG. This is Z, a vector in C to the n. And
désolé, je n'ai pas.
Sorry. And I will erase all the hyperplanes that are obtained using the GJ. Okay, so here again, this is GJ transpose of E1. So here I am erasing finitely many hyperplanes, namely the hyperplanes that are associated to the translate of so it's like, can remark that this is equal to E1 GJZ. And the important thing here is that if you replace GJ by GJ G minus 1 and Z by GZ, then the product is the same. So it's really so this this set of hyperplanes is preserved by the action of G. Okay, so that's the first way to erase hyperplanes equivariantly. Another way to erase not really hyperplanes but subspaces is to consider now this subset. Again, you have a point in EKG and times Cn, and you ask that for any subset of the indices from 0 to k, if J has less than n element, then Z does not belong to the subspace spanned by the Qj, where J belongs to big J. So again, Z does not belong to the span of the Qj is equivalent to GZ does not belong to GQJ, and recall that Qj is Gj minus 1 E1, so that GQj is equal to E1. So in both situations, you have two open subsets of Cn minus 0 that are constructed equivariantly with respect to the G action. I will denote the corresponding open sets, the projection of these open sets. So we get open simplicial subset. The first will be denoted U, and the second one will be denoted U prime. Okay, so at that point, I have indicated two ways to erase subspace inside EG cross Cn in such a way that it's preserved by the G action. And now in both cases, you can consider the spectral sequence associated to the fibration. So you have two. So now I have these two open subsets, and we have associated spectral sequences. The first one goes from the cohomology of G with respect to the limit of the cohomology of Cn minus the union of the kernel of the Cj, sigma j, and this converges to the cohomology of U. And similarly, we have a spectral sequence that now goes, and here the union is over all subset J as above, and you erase the span. And this also converges to the cohomology, but now of U prime. And yesterday I mentioned too quickly marvelous theorem of Bergeron on hyperplane complement. So let me state it again. And now more slowly. Bergeron theorem tells you, it was a conjecture by Arnold, tells you that if you consider something that I will call omega n affine, which is the algebra spanned by the, so this is not very important, this 1, 2 IP, but let's write it correctly. So if you consider all the one form that are of the type dl over L, where L is a linear form on Cn, which is non-zero, I should add also the also one to generate the algebra. Then I will call the algebra generated by this form the affine omega n. The affine, sorry, I should put a dot here. The algebra here, and the Briscoe theorem tells you that now if you project onto, so I will take the limit over a set over hyperplane, all the hyperplanes of the cohomology of Cn minus these hyperplanes, then in fact it's an isomorphism. I should say that Briscoe's theorem can be stated with finitely many hyperplanes. If you erase finitely many hyperplanes and you consider this algebra, then the map to cohomology is in fact an isomorphism. So it's quite remarkable that you can describe all the cohomology only using this algebra. So of course, it remains to have one interesting question that was tackled later by Ulrich and Solomon, is to understand what are exactly the relation between these forms. But already this theorem is quite remarkable, and so when you use it, since we have a cohomology class with values in the cohomology of Cn minus hyperplane, and since if you go back to these two situations, since when you erase hyperplanes, there is no cohomology in degree less than n, bigger than n, sorry. Then the first degree when you have cohomology is degree n, and so the conclusion is that the class S affine yields a class in the degree n minus 1 cohomology of G with values in the degree n part of this algebra. So that was that's essentially what I explained last time at the end, except that now I have explained two concrete ways to erase hyperplanes. And in fact, the goal of the next goal in my lecture will be to compute explicitly a cocycle representative for this cocycle, and the two ways to erase hyperplane will naturally lead to two different cocycle representatives. So let me destroy the suspense immediately and give you the formula and for cocycle representative of this cocycle. So the two ways to erase hyperplanes will eventually lead to two cocycles. The first one, so it's a cocycle of G with values in omega n affine, and the expression is the following. You take n tuple of elements in G, then you associate to this a wedge of form. I should have said somewhere that I will denote omega L, the form I mentioned. And here, lambda J is just the form that really that defines the hyperplanes that we have erased in the first construction. So we are precisely meromorphic, and the meromorphic form are singular precisely on the hyperplanes we have erased using the first construction. So that's the first cocycle. It's an easy exercise to check by hand that this is indeed a group cocycle. So in fact, it's an invariant cocycle. So first you have to check that S affine of, so if you multiply all the elements by G, then what you get here is the action of G on the form S affine of G naught up to Gn minus 1. So that's really easy because you know how G acts on the linear forms. So that's it's immediate from the formula, and also it's a cocycle property. The cocycle property means that the sum, when you go from zero, given n plus 1 element, the sum of, so you apply S affine to G0 up to Gn, but without Gj, so it gives you this form, and this form is equal to 0. And so I should forget, now I can forget that, and the property just follow from that this is equal to 0 for any choice of linear form that are non-zero. And this is a nice exercise to check. You write down the linear form in terms of the others because there is a dependent relation, and that gives you the cocycle property. So let me come back. So this is the first group cocycle that is very easy to write down. Now, and the relations that are here are called the Ulrich-Solomon relation, and they are quite easy to check. And now there is the other way to erase hyperplane that leads to another group cocycle that is interesting to consider too, and that I will denote S affine star. It goes again from G to the N to omega n affine, and it's essentially the same expression except that you replace lambda by L. And so you have to say what is L, and here L is a linear form whose kernel, of course, it does not, only the kernel is important, is generated by the vector Q0 Qn minus 1. And I should say that if Q0 and Qn minus 1 were linearly dependent, then I would put 0 in the definition. So I assume that the Qj are linearly independent. Recall that Qj again is Gj minus 1 E1. Okay, so that's another expression. It's less obvious to check that it is a cocycle, but it's indeed a group cocycle. It's as obvious to check that it is invariant. That's the same. That amounts to what I've said earlier. That the way we erase this when you erase this hyperplane, you erase it in a G equivariant way in EG cross Cn. So that's another group cocycle. And so a first theorem that one can prove coming from the topological side is this. Is that the class S affine yields by the above construction the classes associated to these two cocycles. So in fact, I should say the other way, these two cocycles define the same cohomology classes, which is non-zero and belongs to Hn minus 1 G omega n affine. And so this is less important, but it's just to emphasize how we prove that the two classes are the same, because they come from the same topological construction, and they are non-zero. So I should say that both this cocycle were, I mean, the first cocycle S affine was first introduced by Sczech in his paper where he introduced the Sczech cocycle. In a non-published note, he also mentioned the second cocycle and mentioned that it is a cocycle. He does not give the proof, but he says that he can prove. He has checked somewhere that the cocycle property is satisfied. He doesn't make any relation between the two, but he already considered this. And I want to say that the most important cocycle of both is the second one. So this is, and I will explain now why, because it will be important later, is that the second cocycle has an advantage over the first, is that in unprecise terms for the moment, it extends to the boundary. It extends at infinity. So of course you may wonder what does I mean by that at this stage. I will say it like that, is that in fact you can consider more than just evaluation of the cocycle on G elements, but you can look at this map. Take any n tuple of vectors in Cn, then the map that I have described above. So here I will explain what it is. I want this to believe in the so-called Steinberg module of Cn. I will explain what it is in a minute. And this map is G equivariant. So there is nothing like that if you look at the first cocycle, but for S affine star, you know that you see the cocycle can be specialized by just saying that to G0 up to Gn minus 1, we evaluate this map at G0 minus 1 E1 up to Gn minus 1 E1. So that's the cocycle S affine is a kind of can be deduced from this. And what I call the Steinberg module is the module generated by the symbols V, let's call it V1, Vn, where these are vectors in Cn, non-zero vectors, plus some relations between them. So first relation is anti-symmetry. Second relation is homogeneous. Third relation is that it is zero if the vector are linearly dependent. And fourth relation the one that corresponds to the cocycle relation here. If you have a n plus one vector, and there is a, I should add that there is a G action, meaning that if you consider this symbol, then it's equal to the translate of this. And if you were there at either at my colloquium talk or at the talk of Paul Gunnels yesterday, then you should recognize something like that it looks like modular symbols. And in fact, it's really the same relation as modular symbols, except that what you are considering is tuple of complex vector, not only integral vectors. So that's why I'm talking of the boundary at infinity, because these modular symbols you can think of them as a homology class relative to the boundary at infinity. And in fact, the Steinberg module of Cn can be defined topologically as the reduced degree n-2 of the Tits building of GLMC, which is also the same as the relative homology of the symmetric space associated to SLNC with respect to the boundary at infinity. So we will see this later, but that's why I claim that what we have done here is extend to the boundary, because now we can associate a value not only to a cycle for the group, but to a cycle, to modular symbols that somehow can be thought of as cycle relative to the boundary. So this second cocycle is, in that respect, much more interesting, and as a corollary, we can recover a presentation of ON affine. Why? Because we have this G equivalent map from the Steinberg module to ON affine that is non-zero, and this Steinberg module is irreducible under the G action. So now you get a presentation of the image. So you see the difference between the two cocycles. The first one was easy to check that it was a cocycle just by checking that the differential form were satisfying the relation in the Ulrich-Solomon algebra. And now using this one, we show that all the relations in the Ulrich-Solomon algebra are the one that are obvious. So that's the difference between these two cocycles. So
may I ask a question, please?
Yeah, of course.
This is really intriguing. So this relationship between modular symbols and relative cohomology of well configuration spaces or complements of hyperplanes, how explicit is it? Does it? So yesterday in Paul Gunnels' talk, the relation that you wrote down, that was essentially for saying that modular symbols generate some cohomology group of this locally symmetric space associated with the SLN Z in this case. So is this relation at the level of cohomology groups, that some cohomology group of a locally symmetric space is equal to or isomorphic to relative cohomology of these configurations?
There is no locally symmetric space because there is no lattice here, but it's really the cohomology of the globally symmetric space relative to the boundary at infinity. And this I will discuss more at length in the fourth lecture when I will describe compactifications of symmetric spaces. And so you will really see the Steinberg module or the modular symbol as occurring like that. But for the moment, I just want to give some motivation to go into computing this cocycle, and so motivation would be that we get algebraic relation from the topology of the group GLNC, because the irreducibility of the Steinberg module is really related to understanding the topology of GLNC. And on the other hand, you have this algebra form that could appear unrelated, but are related by this cocycle.
That's okay. That's very nice. Is there some? Will there be some statement about Hecke equivariance? Because on one side you will have Hecke action.
There will be Hecke action when it will be modular symbol. Associated to a lattice in. But here there is no Hecke action. But somehow. I tend to think as a Hecke action as the fact that this map here is in equivalent under the GLNC action. So you have more than just a cocycle. You have a map on the modular symbol, which is equivalent with respect to the GLNC action. And now, when we will globalize this and work after averaging by lattices, then this GLNC action will be replaced by understanding the GLNQ action, that will explain the relation with the Hecke operators. But for the moment, there is no Hecke operator. I mean, there is no arithmetic at this point.
Great. That's
okay. Maybe we can discuss. I just want to end this.
Yes, please.
By discussing now the trigonometric elliptic case that will lead to arithmetic. So let me discuss the. These two cases, and now in these two cases, we are considering a family of abelian group. Groups with one-dimensional connected fiber. So, in brief, either A is the multiplicative group, so that I will prefer to see as C mod Z, because then you average by Z, not a lattice, but at least a discrete subgroup, or A is an elliptic curve or a family of elliptic. You authorize a family of elliptic curve. So sometimes I know some of them ask what is the more general situation. You could consider a higher dimensional family of abelian groups. The thing now is to make a product so that you have an action of a big group, of a big arithmetic group. So what you do is you consider T over S, the n-fold fiber product of A over S. So then now you can consider a group G, but not GLNC, of course. GLNC is too big, but GLNZ acts on T. It acts linearly, and because it preserves Z or Z plus tau Z, I mean, in the elliptic case, then it gives an action on this n-fold product. And what we will do is essentially play the same game. We will consider the equivariant cohomology of T minus some points. So to describe the points I will erase, let C be an integer. Then I can consider what I will call the C torsion divisor in T. This is an element D in the equivalent, the H0 equivalent of this the C torsion point inside this family T. So example, and you can really stick to this. You can take D equals 0. Just take the 0 section, and then the degree of D, because there is only one torsion point, the 0 point is 1. In general, I will call the degree of so maybe I should have said this before. If I see D as a G invariant Z linear combination of C torsion points, then the degree of D is the sum of their coefficients. Okay, so really in the fiber you have C torsion point. You take some combination, linear combination with integral coefficient of them. So of course you can just take the 0 torsion point. It has degree 1. We have already encountered in Sullivan's theorem. So let me say it here. Let's say in the case A equal E, then we can consider all the C torsion points minus a certain multiple of the 0 torsion points. Since in the case A equal E, the fiber is 2n dimensional, I take C to the 2n times the 0 torsion points. So this divisor has degree 0. Okay, but of course you can think of many other divisor of degree 0, but this was the one that arises in Sullivan's theorem. So now let's do again equivalently what we have done with in the first lecture. So recall the Thom isomorphism. The Thom isomorphism in degree 0 identifies this group H0G of T of C with the equivalent cohomology in degree the dimension of the fiber. So it is 2n of the whole space relative to T minus TC. This is precisely the what says the Thom isomorphism in that situation. We have a T bundle and we erase finitely many torsion section. And now we can consider again the long exact sequence. Of the pair T minus TC. And this long exact sequence, I will consider this part, 2n minus 1 G of T to Hg 2n minus 1 T minus TC, and then go to 2n G T relative to T minus TC, and finally go to SH2NG of T. And so we have a Thom class here. We have the Thom class associated to our divisor. So I will rather say that here we have the class of our divisor by the Thom isomorphism. And the lemma tells us that I will distinguish the trigonometric case. This lemma is the analog of the way we constructed the affine class, is that the image in AG20 of D is rationally 0. So what, each time you pick up a divisor, then in the trigonometric case, you take a 0 class in the equivariant cohomology in degree 2n. It's imaged in here. So, and in the elliptic case, the image in of D is 0, is rationally 0, if and only if the degree of D is 0. So again, we are now considering another situation where if you want the image of D is something like the Euler class, and we are asking ourselves the question, where is the Euler class 0? And if this is 0 here, then it means that we can lift the element D into some element in the in this group, which is the analog of what we have done when we have considered LG of 2n-1 of C minus 0. So that's the two statements of the lemma. I can explain briefly where it comes from. So the first case, where the trigonometric case, we know that D is, by definition, G invariant. It's a G invariant torsion section. So its image in the equivariant cohomology, in fact, survives in the first step of the spectral sequence in H0 of G, H2n of T. It's really an invariant. It really gives an invariant class in the cohomology of T. But in the trigonometric case, this is 0, since T, which is C star mod n, is affine. So in that case, it's 0. The class is 0 for some trivial reason, which essentially amounts to which is very close to what happened in the affine situation, in the CN situation. In the second case, it's more subtle, but the statement is precisely a reformulation of Sullivan's lemma. The fact that the degree is 0 precisely says that that the projection to if you consider again the proof of Sullivan's lemma, that what we were using is precisely that the divisor that was the C torsion point minus C to the n 0 was of degree 0. That was exactly what we used in the proof. And so if you redo the same proof but using any degree 0 divisor, then you will get you will get the same statement. So that's why. And if you don't quite see it, just take the divisor I mentioned. The important thing is to have such a degree 0 divisor. And so in the end, the end. If we fix some divisor, so let me fix one with, of course, with degree of d equals 0 if we are in the elliptic case, then we can lift d to the equivalent cohomology of degree 2n minus 1 of t minus tc. So again, we have a class, but now we erase a priori, in the elliptic case, we need to erase more than just one point. We need to erase finitely many points that have a degree 0. And there is something annoying in that I have completely ignored in the affine case. I'll tell you later why, but that I don't want to ignore anymore, is that this class is not canonical because we are using the long exact sequence and there is a kernel, and the kernel is precisely the degree 2n minus 1 cohomology, equivalent cohomology of t. And there is no, this cohomology is non-zero in general, so there is really a kernel. In fact, we can kill this ambiguity, and this a similar thing was discussed in Romiar Sharifi's talk yesterday, where he used the trace map. So exactly that's what we do to kill the ambiguity. So to kill the ambiguity in the lift, we can consider the map, which is multiplication by some integer. So I will use small s as an integer. You'll see later why, but this is multiplication by a positive, an integer, a positive integer. Again, this gives a finite cover map, and this map induces a push forward map that goes from the equivalent or not. In fact, it works. It induces a push forward map. So to be completely rigorous, I should say that to build this map, I should first restrict to the cohomology where I erase SC. I will take S to be prime with C, with a C torsion point. So I can restrict the cohomology group to T minus all the SC torsion points. And then when I multiply by S, the SC torsion point becomes C torsion point. So the map here, in fact, should be really a restriction map composed with the push forward map here, but I can just forget it and consider this push forward map here. Okay. And now, in general, so for example, if S is prime to C, note that the push forward of the TC minus C to the n 0 is equal to TC minus C to the n 0. I mean, what I'm saying here is that the push forward map can be considered in all the cohomology group, not only T minus TC, but also just T or just TC. But if S is prime to C, then it mixes up the C torsion point, but it preserves the global, it preserves 0, and it preserves the whole set of C torsion points. So it preserves the class, the fundamental class of TC minus C to the n 0. And in general, if you take any D, there exists S such that you may have to I mean, to add more prime relation, but you can always find an S that will permute the element in the divisor D, but globally preserve D. And so in the end, we can really consider the classes that are preserved by the push forward map. And so this gives the following definition. I denote by this the subspace of the equivariant cohomology, and I could consider also a equivariant cohomology of T or standard cohomology. The subspace of classes mapped to 0 by a power of this. So it's almost you can think of it as being preserved by the push forward map. So the class D belongs to HG. So after the term isomorphism, it belongs to this. And in the elliptic case, it turns out that AG is 0 because the fiber are tori, and the push forward maps on k-dimensional tori I acts by k. So it cannot act by the trivial by eigenvalue 1. So there is nothing in this cohomology. So it kills the kernel of the in the long exact sequence. So in the elliptic case, D as a canonical lift in this group. So there is a way to lift canonically the class to this equivariant group. In the multiplicative case, or in the trigonometric case, I mean, the lift is only defined in the trigonometric case. The lift is only defined modulo sorry, modulo this part, which can be non-trivial because now T is a as a non-compact fiber. So now there can be a kernel, and but in any case we have a class, and we can control the defect of canonicity. And to conclude for today, from this class, after erasing hyperplanes, but now when I mean hyperplanes, I mean elliptic hyperplanes or hyperplane in C star to the n, so multiplicative hyperplanes. Then we get classes trigonometric D and elliptic D in the cohomology of degree n-1 of the group G. Here the limit is over some set of hyperplanes of the cohomology of the fibers. The fiber meaning is T minus some collection of hyperplanes. So, and when I say hyperplanes, sorry. No. So, yeah, Hn of T minus, so here, and union A are some tertian points, and you take K minus 1 of A. So it's affine hyperplanes in T. So you have a collection of affine hyperplanes. You take the limit over these hyperplanes, and now you have this cocycle. So this is not very satisfactory because it's still cohomology group, but in fact what we can prove is that there is some kind of Briscoe theorem if you restrict to the invariant part here, and you can replace by meromorphic form. And yeah, oh, I'm sorry for the delay. So let me just finish by stating two theorems, and that I will discuss later. So the first theorem is theorem 2 in the trigonometric case. So D, if you take any divisor, then you associate to this a trigonometric cocycle that belongs to this. And which is canonically defined modulo the regular forms. And in the elliptic case, D, if you start with D of degree 0, then you end up with an elliptic cocycle that is canonically defined in that case. So I've rushed today, sorry. So my next goal now is to forget about the topological construction and to go into more automorphic form stuff. So I want to in my next lecture I will describe how to build differential form representative for all the classes I have described. This will this will lead to explicit representative for this cocycle, and then I will compute this cocycle and see what it gives. So this will end the topological story. And sorry for the rush and the late. So I'm stopping now. Sorry.
Well, thanks, Nicolas, for your very nice lecture. Are there any questions? Tony, your hand is raised.
Thanks. Yeah, so I didn't really quite catch what was the difference that in the trigonometric case it was only well-defined up to this thing, and it was completely well-defined in the elliptic case. Can you explain that again?
Can you repeat?
I didn't. Oh, sorry. Okay, I didn't quite understand why it was that in the trigonometric case, the cocycle was only defined up to something, and then the elliptic case. Yeah,
the thing is that in the end, in the long exact sequence, the term in the kernel is H2n-1t, H2n-1t equivariant. Okay, and now I consider the part that is fixed by the action by S on the fibers. In the elliptic case, the fibers are compact, and so the action by multiplication is constrained. You cannot have a class that is fixed by the action by multiplication. But in the trigonometric case, the fibers are C star to the n, so it's non-compact, and there are classes. For example, if you work in C mod Z, it's better. It's easier to see it in C star. If you work in C star, dz over z is fixed by multiplication by an integer, and so so it's not this group is not trivial. This and in general on the cohomology of Cn mod Zn, you will have invariant forms, and these invariant forms will be fixed by multiplication by an integer. This cannot happen if the fiber is really a compact torus.
Okay, thank you.
Udi, you have a question?
Yeah. Hi. It seems to me that there is a fourth case that maybe is interesting, and this is where the elliptic curve that you take has complex multiplication, and you can take for G, GLN O of a quadratic imaginary field. Have you explored this case too? Yeah.
This is in fact, this is quite interesting. This is a very interesting case. Thanks. It will be studied more precisely by Luis Garcia in his talk, and the thing is that now as you expect, it leads to classes of degree. So here you will have a gamma, which will be a finite index subgroup of SLN of OK, and you end up in a meromorphic form of degree n in E, where E is as complex multiplication by e to the n, where E has complex multiplication by OK, and yeah, this is an interesting case, because then if you evaluate on some torsion point here, then you get interesting cohomology class for this generalized Bianchi groups, and what Luis will explain is that looking at this construction, and as I will explain, there will be product of theta function here. Then in fact you can explicit L values of degree n extension of CM field, special values, critical values of L function associated to degree n extension of CM field. You can express them as sum and product of special values of of polynomial of special values of E1s.
So this would be related arithmetically to cuts in the same way that the previous example is related to the Lin-Ribet.
Exactly. Except that, so the relation with cuts will be more explained in a quite different framework by Johannes Spreng. If you just want to prove the algebraicity, then in some sense you don't really need the full powerness of this kind of cocycle. It's a bit what I explained at the beginning. There are scalar cocycle, and there are cocycle with values in spaces of function. If you can prove that this scalar cocycle is algebraic, then it's enough to prove the algebraicity of these critical values of L function, and that's exactly what Johannes Spreng will do by getting from sophisticated construction that he will explain better than me. And this other perspective here tells you somehow relation between these L values and product of E1. So it's a bit like instead of proving the Ling-Ribet, you really prove that the L value can be a product of essentially of cotangent function evaluated at some particular point. So it's both. I think both things are quite interesting, and okay, we'll see this in the comparison between the talk of Johannes Spreng and Luis Garcia.
Thank you very much.
Are there any other questions?
Yes, just a small comment, if it's okay. So I just wanted to understand this complement of hyperplanes better, and in relation to Arnold's theorem. So the first question is, what is pi1 of this complements of hyperplane arrangement?
Oh, what is pi? I don't remember. I mean.
So I can give you in terms of so one complement of hyperplanes is basically configuration space of n points on C.
Yeah.
And that's the original Arnold case. And in that case, the pi1 turns out to be the braid group. And then, I mean, Arnold's theorem is that the entire cohomology algebra is the exterior algebra generated by one forms, and one forms are these easy logarithmic forms that you wrote down exactly. But the important thing is that these one forms satisfy infinitesimal braid relations. I mean, this is where the pi1 thing comes in, and this is the important thing in physics or in two-dimensional conformal field theory. So I'm just wondering, in this case, what is pi1, and if and what would be the analog of the infinitesimal action of this pi1 on these differential forms?
I don't know, because that's really not the way I think of it. So I haven't. Yeah, I have nothing to say about this. Yeah. Sorry.
No, that's okay. Thank you.
Are there any other questions?
I had a bit of a question, if there's time. I was just wondering, so it seems like you really exploit these like formality isomorphisms between like some cohomology complexes and like complexes of differential forms a bunch. And I guess in all these cases, by like work of Sullivan and stuff, there's like formality holds even with rational coefficients. So I was wondering, do you exploit this in any way later on, like these formality isomorphisms with rational coefficients to prove rationality? Nah? No.
Later on, so in fact, starting tomorrow, I will really give explicit differential forms representative of the term form and then of the transgression of the term form using the Matta equivalent formalism. And so I don't. I mean, I don't need any formality theorem, because I have a very nice complex that does the job. I mean, I use a standard differential form complex that does the job for me. And here there is a nice differential form that will really be, I mean, in my opinion, the right function, the right differential form to use to compute this.
Right.
The right representative of the class. I mean, more than the cohomology class, I want to have a cocycle. So I want a differential form representative that is a nice one, and I will try to convince you tomorrow that the nice one is given to us by the Matta equivalent constructions, and so that's what I use. I don't have to use any formality or trying to find another complex that computes the yeah, that's but if I don't really understand everything in Nori's work, but if I understand correctly, that's something he does to construct the scalar cocycle. Yeah.
Okay, thank you.
Are there any other questions?
It's just a quick. I was looking for a reference for Sullivan's theorem yesterday, and I couldn't find anything except there was one paper in French, which I guess was Fibre vectorial SLNZ at class trivial. Is that the one? I
Yeah.
might have completely butchered the title, but there's no English version, or
That's the one, and
That
that's
one,
and
I
that's
got
that one. That
I'm
one,
sorry.
Baba.
So
That's why I wasn't
That
opening the
one,
video today.
Baba. That one, Baba.
Sadhu, one second, please.
no. So that's the one. That's this paper that is half a page long. It's not a compte rendu. That is. I mean, I gave the full proof, and that's half pages
And
long in Sullivan's paper. And I should say that later on, Bismuth and Shiger gave another proof of this theorem using the matter-equivalent construction. And in fact, what they do is to exhibit a differential form representative of the transgression. So that's what we are. That's really what we will be doing starting tomorrow. But I will more follow matter equivalent directly than Bismuth Shiger. But that's really the same. This idea came from Bismuth Shiger.
Okay, thank you.
Are there any last questions? Okay, well, if not, let's thank Nicolas again for his great talk.
Thank you.